Yeah, okay, welcome back, everyone. So today is our pleasure to have Hachem Kadri, who will be talking about implicit regularization and deep tensor factorization or dynamical analysis. Yeah, thank you, Hachem. Yeah.
Yeah, hi everyone, and thank you, Mumedian, for this invitation. I'm happy to give a talk today at this seminar and share with you some research work I conducted recently on implicit regularization. So I'm Hachem Kadri. I'm a professor of computer science at Aix-Marseille University, and I am a member of the machine learning group. And so the focus of my talk will be on deep tensor factorization. In particular, I will show how dynamical analysis could provide insights into the implicit regularization in deep neural networks. Okay, so feel free to interrupt me if you have any question. So this work was carried out under a collaboration between Aix-Marseille University and the National Engineering School of Tunis. This is a joint work with Kais Aris, Stéphane Ayash, Thierry Artière, and Meher Mouakher. So the research I will present in this talk is a research conducted during the PhD thesis of Kais Haris, who did his PhD under the supervision of Meher Mokhar and me. Okay. So I would like to take this opportunity and thank my collaborators. Let me start by putting this work in its context. So this is a figure, well-known figure about the performance so we can achieve it by different neural network architectures to solve the ImageNet classification problem. And what is important in this figure is to show that the performance we achieved is related to the depth of the networks. So if you can see here, for example, for these two neural networks, this is our shallow network, this is the performance achieved is 28 error. This is the error of classification, 25. And as you can see, we after that we have neural networks with more layers and more layers until achieving this big through performance of 3.5 error rate. And this was achieved using 152 layers. Why this was a very important step? This is because I think for this ImageNet classification task, this is the first time when we have a machine learning algorithm which beat the human performance. If I'm not mistaken, I think the human performance on this task is about 5%. Okay, and one can ask the question: why deep learning achieve big throw performance? Possible answer to this question is that having deep layers, so many layers, this we have better expressiveness, so we have more expressive power of the learning models, and also we can have a good generalization performance. The main challenge is that in classical learning theory, in general, when we have a model too expressive, we don't have a good generalization performance. And in this setting, we can have both, meaning that when the model is very deep, we are more expressive, and also we have a very good generalization. And this paradox is at the heart of deep learning theory. And many research direction have been proposed to try to explain this phenomenon. Okay. Let me start by recalling some known concepts on the theory of machine learning, classical machine learning algorithm. So this figure, we have x-axis is the capacity of the model or the expressiveness, sorry, of the model, and this is the risk. So this is the performance error. The dashed curve is the curve of training error. And as you can see, when we have more complexity, more capacity, the error will, we have less error. Okay. And this is not exactly what we obtain on the test error. So this is the error measured on test data. So when we increase the capacity of the model, so the error will we have this decrease of the error, and after that, at some point, we have an increase of. And in this part, in general, we said we have overfitting. So overfitting, so we have a situation where the training error is small, however, the test error is high. And to study theoretically a machine learning algorithm, we derive generalization bound, and we have many ways to derive a generalization bound. And in general, we obtain a result similar to that. The true risk, so this is the error, and the test error, if you would like. And this is the train error, and we have the true risk is less than the train risk plus another term, and this term will depend on the complexity of the model and also the number of training examples. Alpha is is the coefficient, and standard techniques, so the alpha will be equal to 1/2. Okay, and we are happy with this result because it shows that when the number of examples tend to infinity, so the true risk is less than the train risk, and so minimizing the train risk, we can control the true risk. In the situation where the complexity is high, in this case, minimizing the true risk, the train risk cannot be a way to control the true risk, and so we can have overfitting, and the true risk can be high, and we are in this situation. And in many standard machine learning technique, we can see this behavior. Okay. However, in deep learning, this is not the case. We are in the situation where the number of learning parameter is very, very high. So it's much larger than the training examples. So we have a very high complexity, and also this high complexity lead to a good generalization. And we don't, and this is the main question: how deep neural network generalize way? Because this configuration does not fit the previous setting. So many line of investigation have been proposed. Among them, I can cite double descent, benign overfitting, and implicit regularization. And this work will be on implicit regularization. Before talking about implicit regularization, let me give quickly the intuition of double descent and benign overfitting. So double descent, the idea is the following: the intuition behind this, that in general, so the curve we have this following form. So this is, like previously, this is the test error, and this is this is the train error, and this is the test error. So we have the decrease, and after that increase of the error. But when you arrive at a certain point here, okay, we have another decrease of the error. This is what is called double descent. And in some sense, deep learning, we are in this part of the figure. So we have a very high capacity, and in this situation, we have also a good generalization performance. And the question after that is to characterize this double descent phenomena, and to see which kind of machine learning algorithm, with which kind of machine learning algorithm we can have this kind of behavior. Benign overfitting is related also to this question of to this idea of double descent, but The starting point maybe it's a little bit different in the sense that what we already know on overfitting is what is represented here in this figure in this plot, which is called here catastrophic. So here we have the data points. The true curve is this one, and as you can see, the learning curve is the curve in blue. And if we were this with this curve, as you can see, we have a zero, very small training error because the curve here we have the curve that is for all these points we have exactly the same value. Okay. However, if we would like to use this curve to predict another point, for example, here we can see that the prediction will be very, very bad. And this is what is catastrophic. But some recent work showing that we can find other other configuration with the situation when we have zero training error. And so we can have, for example, this kind of situation, which is called a tempered in this case. So we have, as usual, we have zero training error. So we have the curve here. As you can see, the train error is zero, very small, and this curve is not very similar, but is better than this one. And there are also sometimes situations where we have zero training error and the learning curve is similar to the curve we would like to the true learning function, like illustrated in this figure. And this is what is called benign overfitting. So we can here have zero training error and also good generalization performance. And so there are research work. I think the first paper was proposed by Bartlett in 2020 about this phenomena. And after that, there are a lot of work about trying to investigate and try to find machine learning algorithm that and find the situation where we can see this benign overfitting behavior. Okay. The idea of implicit regularization is a little bit different, but it is also related. I'm not saying that these three lines of investigation are completely different. It is not the case. There are connection between them, but maybe the starting point and the starting idea is different. In implicit regularization, we don't fix, we have a large hypothesis space. Okay, this is the hypothesis space. So our learning algorithm could find any function in this hypothesis space, but the learning algorithm will implicitly find solution in a subspace of this hypothesis space. So as here, for example, this is the solution space. In general, if we can have explicit regularization, and when we add explicit regularization in, we explicitly fix what kind of a subspace the learning algorithm will try to find a function in this subspace. However, when in implicit regularization, we don't have any constraint on the subspace, but the way of the optimization, the way how the algorithm will learn, implicitly will find solution with some low complexity. And the main question, which low complexity, which measure of complexity will be minimized by the learning algorithm. What I will discuss and will show today is research work on implicit regularization in the case of matrix and tensor factorization. Do you have any question? Okay, no question, so I can continue. So let me start by implicit regularization in matrix factorization. So here the problem is to recover a matrix which has missing value. So we have a matrix B. Okay, in the matrix B we have a missing value, and we would like to recover this missing value. Standard way to address this problem is to do some low rank approximation. For example, we will approximate the matrix B using the product of two matrices, A2 and A1. Okay. And in general, we choose A2 and A1 such that the number of column of A2 and the number of line of A1 is small. And this means that A2 and A1, the product of this matrix, is a low rank approximation of the matrix P. Okay. So we minimize an error like this, and we approximate the matrix P using a low rank matrix. There is this paper by Gunasekar in 2017 who tried to who studied this problem, but without constraining the rank of the product matrix A2 and A1. So we minimize this problem. We can use a neural network to minimize this this optimization problem. And they choose the situation where the number of lines and the number of column and number of line here is high. Okay, we don't have any constraint. And they observed that there is an implicit regularization toward toward norm minimization. By norm minimization, I would like to say that the solution found after that is a solution with low rank, and it is related to the nuclear norm minimization of the product matrix A2 and A1. And they conjecture that with small initialization and small learning rate, matrix factorization here, depth is equal to 2 because we consider only the multiplication of two matrices, converge to a solution with minimal nuclear norm. Okay. So in other words, we don't have any constraint on the norm of the product matrix, but when we solve this problem using neural networks, there is an implicit regularization such that the neural network will find solution with minimal nuclear norm. After this work, Aurora and the co-authors pushes the analysis further and consider the deep sitting. So they consider instead of having the multiplication of two matrices, we have here the multiplication of K matrices. And they solve this problem. And they observed that in this sitting, so when K is larger than 2, there are sittings where deep matrix factorization drive all norms to infinity. And so deep matrix factorization in this case means that it doesn't induce implicit behavior towards norm minimization. So the question in this case, which complexity is minimized? So they provided another alternative, and they showed that with small initialization and small learning rate, in the deep case, the deep matrix factorization converges to a solution with minimal rank. To justify this claim, they did a dynamical analysis of the singular value of the product of the matrix. So here we have K matrix, AK multiplied to A1, and this is the deep matrix formulation. And they consider the singular value of the product of these matrices. So sigma R is the singular value of the matrix A. We don't have any constraint, so this means that the columns of these matrices are not restricted. So we have a full, and here we don't have any full rank, okay, full dimension mean. And they try to find a dynamical analysis of the singular value. This means how the singular value evaluate over time, and find this equation. The derivative of sigma r at time t is proportional to sigma r to the power 2 minus 2 over k. K here is the depth of the matrix factorization. And the way this is figure show that how the singular the behavior of singular value. And as you can see here, for example, we have only 5 singular value which emerged during training, This means that the learning algorithm will find matrix A with rank equal to 5. Let me just add some comment about this equation. So what is the meaning of this equation? This means that when the sigma here, when the singular value is small, the speed, so the evolution rate of this singular will be small, okay? And when this is high, so the sigma, so the evolution will be also high, okay? And this means this is the reason why we have many eigenvalues, many singular values will be will not will have a value very near to 0, and only some of them will emerge and will have a high value. Okay. This is the situation in matrix factorization, but in matrix factorization we don't have nonlinearity, and we know that neural networks we have a nonlinear model, and after each layer we have nonlinearity. To extend the analysis to the nonlinear case, one possible solution is to see tensor factorization. Here is CP tensor factorization. So we have a tensor. CP tensor factorization is the decomposition of the tensor on the sum of rank 1 tensor. So this is rank 1 tensor. You have the outer product of 3 vectors. And this is also a rank 1 tensor. I will use the term block for a rank 1 tensor of the CP decomposition. So for me, this is the first block of the decomposition, and this is the R block of the decomposition. For the CP tensor factorization, the rank here is the number of rank 1 tensors. Okay, the minimal number of rank 1 tensors that allow us to compute the original tensor. Why it is interesting to consider tensor factorization? Because we can show connection between this decomposition and a certain type of neural networks with a nonlinearity. This is was proposed in the paper of Razin and co-author in 2021. So this is just to illustrate the idea. So if we consider images, and after that we do one hot encoding, and consider some kind of locally connected network and some kind of nonlinearity, so specific nonlinearity, we can show that this kind of neural network corresponds exactly to the CP tensor factorization. Okay. So more formally, we consider the following optimization problem. So this is our tensor we would like to approximate. This is the CP factorization. We have sum from 1 over R, and this is one block. This is one rank, tensor with one rank, having one rank. Okay, outer product of vectors. So this is a vector, and this is outer product of the vectors. And the goal is to find this W. Okay. Since we are studying implicit regularization, we don't have any constraint on the rank. So we consider here R is large enough. We don't have constraint. And in Razin, in the paper by Razin and co-author, they also did a dynamical analysis, but now on the norm of the block. So by block, as I said before, this is the rank 1 tensor. You can see this means this block, the outer product of the different block. And so they did analysis of the norm of each block of the decomposition, and they found this kind of result. The derivative of the norm of a block of decomposition is similar to the norm of the block raised to the power of 2 minus 2 over n. And so similarly, this means that if the norm of the block is high, so the evolution will be high, and if the norm of the block is small, the evolution will be small. And this means that after learning, only some norm of the blocks will be high. And this means that many of the blocks here in this sum will be equal to 0 or near to 0, and we have only one of them with high value, and the rank is equal to the number uh, of uh, of blocks such that norm is not near to 0. And this justify implicit regularization toward low CP rank. However, this study has some limitation. One limitation is that the CP network is shallow. We don't have any notion of depth here. Let me go back to the slide about the figure, about the CP decomposition. So this is the CP decomposition. We have this is the sum. This is the associated neural network, and we have only one layer. We don't have notion of depth here. Okay. And so one can ask the question, is there a way to introduce depth into tensor factorization and study the effect of the depth on the implicit regularization? Because we know in deep neural networks, the depth has an effect. So it is important to try to characterize this effect of depth. We can also ask another question. What happens if we choose another tensor factorization? Which implicit regularization we can have in this case? And in my talk, I will try to answer to these two questions, and I will consider deep CP factorization, and also I consider also another tensor type decomposition, which is the Tucker decomposition. It is of note that there are other tensor decomposition which was considered in the literature. For example, hierarchical tensor decomposition, and also in this paper by Razin and co-author, they showed implicit regularization with this decomposition. But my talk, I will focus only on the CP and Tucker. Okay. Let's move to the CP decomposition. Do you have any question?
Yes, I have a question, if I may.
Yeah, sure.
So you showed all this dynamic equations for matrix norm and also singular values.
Yeah.
Are these equations derived from some equation, or is it like empirical fitting?
No, this is derived. So yeah, thank you for the question. Maybe yeah, here for example, I say that with small initiations and even here I say that I think under some maybe was missing, but yeah, this to obtain this kind of result we consider the analysis of the gradient flow. Okay. So the gradient flow, which can be seen as approximation of the gradient descent when the learning rate tend to 0. Okay, and we have to add some assumption. I will discuss some of this assumption in the next part of the talk.
I see, thank you. But so then your update algorithm doesn't have like stochasticity. So it's like a deterministic gradient flow.
Yeah, exactly. Here we consider that we have gradient flow, and we consider the situation when we have small initialization and small learning rate. And this is why the analysis is based on the notion of gradient flow, which can be seen as an approximation of the gradient descent.
Okay, thank you.
Thank you for the question. Any other question? Okay, let's start by the CP decomposition. And I will show you here the work which about implicit regularization with polynomial growth in deep tensor factorization. And this work was published at ICML 2022. The idea is simple. Since we would like to add, the main point here is to add a notion of depth. And since we have CP decomposition, which allow us to have a kind of neural network with some kind of nonlinearity, but we cannot have on a notion of depth in this decomposition. This is already, we have already this result in the literature, and we have also the second result about matrix factorization. But with matrix factorization, we have the notion of depth, but we don't have the nonlinearity. The idea here is to consider deep CP decomposition by combining deep matrix factorization and the CP factorization. So we have, in this case, the following factorization. This is the tensor. As you can see in blue is the CP decomposition of the tensor. And since we are in overparameterized regime, we add here we add the multiplication of different matrices, okay, like in deep matrix factorization. So we have this multiplication of this matrix will be multiplied by this vector, and this will be first vector of the first block of the decomposition, okay? And in this case, we can move, and so we can modify the notion of deep. This would be the number of these matrices used in each mode. Mathematically, we can write this decomposition as follows. This is the sum, this is the CP decomposition, okay? This is the outer product to have a rank 1 tensor, and now we have the product of many matrices times vector of each consisting of the outer product decomposition, the rank 1 decomposition of each block, okay? And so here K will be the depth of the composition. If you would like to see what kind of neural network this corresponds, so we can design we can have the following neural network. So like in the CP decomposition, we have one hot encoded inputs, and now we have the different matrices of multiplication of deep matrix factorization. So this is why we have the notion of depth. So we can have here different matrices, and after that we have the one times one convolution and the outer product pooling. This is the standard operation in CP decomposition. Okay. So what is important to mention here? So it is true that we added a depth here, a notion of depth. So we have a multiplication of different matrices, but it is true that the nonlinearity is only at the end of the network. So we don't have nonlinearity for each layer. So here we have the multiplication. So we have different layer, and between this layer we don't have a nonlinearity. This is since it is like in deep matrix factorization. And we try to analyze the behavior of this decomposition over parameterized method. So first result is the following. We can find some invariance during the learning of these parameters. So now the parameters is the CP decomposition. So this is the vector W, and also the matrices A1, AK for each mod is also parameters. And when we do the optimization, so we optimize over W, and we optimize also over A. Okay, and we have this first result. The difference for each block here, the difference between the norm of each matrices at time t is equal to the difference between the norm of these matrices at the initialization. So this means that the difference between the norm of each matrices stay constant over time. This is also the case for the vectors W. The difference, for example, see for this block, if I take the difference between the norm of this block, of this vector, and the norm of this vector, this difference stays constant over time. So the same value as initialization. And also we have the same result between the difference between the matrix, the norm of the matrix, and the norm of vectors. This invariance, this is which allows us to find implicit regularization. So this means that there are some constraint, implicit constraint during the learning process. So using the same kind of analysis, we consider the gradient flow, and we can show in this case the following result. The derivative over time of the norm of the block in this case will be similar to the derivative of the block to the power, raised to the power, the norm of the block raised to the power 2 minus 2 over n plus k. K here is the depth of the factorization. Let me go back to the previous result. So we have the previous result is this one. So we have exactly the same result here. The only difference is that now we have here plus k. And this is interesting in the sense that this shows that when we have more depths, the implicit regularization is more pronounced. So this means that when the norm is large, the block, the norm of the block will move faster with larger k, and when the norm is small, is the norm of the block will move slow. Okay. This result is about the norm of the outer product of W. If I go back to this decomposition, so this is the result is about this tensor W, outer product W1, and outer product W2, outer product W3. But what we are approximated, what we are learning is the tensor product when considering the matrices. This is why we have also another result showing that the norm of the block when considering the matrices AI is always lower than the norm of the block without the matrices. So the norm of each block of this block will be always smaller than the norm of the block without considering the matrices. So if we have implicit regularization toward low CP rank for the decomposition without the matrices, this automatically induces implicit regularization over the low rank, CP low rank, when we consider the decomposition with the matrices. And this is the explication of these results. Let's see now if we can observe this behavior in practice. So this is some numerical simulation using synthetic data. Here we generated a fourth order tensor. Each dimension is equal to 10. Okay. The true CP rank of the generated tensor is equal to 5. Sorry. Okay. And this means that, yeah, this is generated. And so this means that when we generate, we consider that we have a tensor which can be approximated with the sum of 5 rank 1 tensors. And now in this figure, we show the norm of the blocks of the decomposition. Here, in the case when depth is equal to 0, depth is equal to 1, and depth is equal to 3. And you can see that the evolution of the norm of the block along training, depending on the depth. When depth equal to 0, we have a lot of norm of blocks with high value. We increase the depths. We have less norm of the blocks with high value. We increase the depth, and here we can see that we have only small blocks which emerged. Okay, so this shows finally, because when we have small number of blocks, this means that the approximated tensor is small, rank tensor is small. Okay. This shows clearly the impact of the depth on the implicit regularization. This figure also illustrates this phenomena. So here we have the depth from 0 to 5. Okay, and here we each point here is an experiment, okay, obtained with different initialization. The color here is to the color represent the test loss. So if the color is green, this means that the test loss is small. If the color is red or purple, this means that the test color is high. So when you do the decomposition, you can see the depth is equal to 0. We obtain many solutions such that the number of blocks which have large norm is high. Okay, and when we increase the depth, for example, here for 5, most of the solution here, the number of blocks that norm is high is very small compared to the one obtained when depth is equal to 0. And you see that we can also obtain a solution with here the point is green, so the solution is a good solution. So the test error is small. Sometimes having a strong consent doesn't mean that we will have a good performance, and this is the reason why you have some points here with in red or in purple. This means that for this experiment, we obtained a higher test loss compared to the other one. Okay. This is additional experiments in on real data. So MET UK and CCDS. Okay, and also we observe the same kind of results. The number here of blocks when the depth is equal to 0, we have here 60, and when we have larger depth, the number of blocks emerged after training is only here around 20. And this result also to show the impact of depth in the implicit regularization and on the rank of ODCP decomposition. Any question about this first part of the talk? There is no question, so I can continue. And the second part is similar to the first part, but the main question here is what happened when we consider another tensor decomposition. And in the second part, we will consider two-curve factorization. So two-curve factorization, it is well-known tensor factor decomposition. So this is the idea is the following. This is the initial tensor. We can approximate it by a core tensor. This is the tensor G. And the core tensor will be multiplied by matrices for each mode of the core tensors. In general, when we use tensor decomposition is to compress the information. And this, when we would like to do compression, we should that the core tensor is small. So the dimension of the core tensor, in this case, will be much smaller than the dimension of the original tensor. But since in our work, we are interested in implicit regularization, so we don't don't add any constraint on the core tensor, and this is why we have also a core tensor with dimensions equal to the dimension of the initial tensor. Mathematically, two-curve factorization can be written like this. So W, if this is the initial tensor, is equal to J, the core tensor, and we have here multiplication for each mode. It is multiplication for the first mode with matrices V1, V2, and Vn. Okay. When we consider two-curve decomposition, we have the notion of multilinear rank. How the multilinear rank is computed? So it's computing as follows. This is the original tensor. For we can do different kind of matricization. So matricization over the first mode, we obtain for these matrices. We have, so we combined, so this is the slices of the matrices over the first mode. After that, we concatenate the slices and we obtain this mode 1 matricization. We can do the same thing with the other mode of the tensor, and we have different mode of matricization. The multilinear rank, so is a vector containing the rank of each matricization. So we have rank matricization over the first mode, just until the rank of matricization of the mode n. This is the definition of multilinear rank. Since we would like to study implicit regularization in deep learning, we consider deep Tucker factorization. So the idea is similar to the deep CP factorization. So this is the Tucker factorization. And to have overparameterized model, we added a multiplication of matrices. And these matrices will be multiplied for each mode of the decomposition. Okay. And so now we have the Tucker factorization. We have the core tensor, the transition matrices V, so the core tensor J, the transition matrices V, and each V is a product of matrices A times a vector W. So J, V, and W are the parameters. And when we do the optimization, the goal is to find these parameters. This is the neural network corresponding to the deep Tucker model. It is similar to the one of the deep CP factorization. CP factorization, so let me go back here to the decomposition or the initial decomposition of the Tucker factorization. This is the Tucker factorization. So the CP factorization can be seen as a particular case of the Tucker factorization. If we consider that the tensor, the core tensor J is diagonal, we have all the value is equal to 0 and we have only 1 at the diagonal, we can recover CP factorization. This is the reason why we have a similar neural networks. The main difference here is here. In the final layer, which is the we don't have identity, but we have here the core tensor G. This is the core tensor G. But the first part of the network is similar. We have this is the matrices of deep matrix factorization. Okay, and after that, this is the transition matrices constructed by the vector W1, WD, and so on. Okay. So we have similar neural networks. The main difference is that the final layer here it is a full layer of parameters. And we can also study the dynamics of gradient flow in this case. And we have also a result about the invariance. The result is the following. The derivative of the norm of W is equal to the derivative of the norm of the core tensor for a slice. It is equal to the derivative of the norm of the matrix. Maybe I can go back to the decomposition. So this is the core tensor. What by slice, I mean that we take only a matrix of this tensor. So we fix we fix for the number of size. For example, slice position 1 will be this matrix. Okay, and we have so the norm of this matrix. The derivative of the norm of the matrix is equal to the derivative of the vector, associated vector here, and is equal to the derivative of the matrix here. This is the invariance we obtained, the norm square. Using this invariance, we can show the following result. The derivative over time of the slice of the core tensor is less than this is a scalar alpha times the slice of the core tensors to rise to the power kn. K here is the number of the depth of the factorization, and it is also larger to this term. Okay. The main difference is that we have different term here, alpha and beta. Okay. In the paper, we can find the exact value of these terms, complicated terms. Okay. This is why I didn't report this term in the slide. But let us study this result. So this means that okay, when the block of the norm of the slice, this is the slice, as you can see, we fixed here for the value Rn. So this is for the slice. The norm of the slice is when the norm of the slice is high. The norm of the slice is high. We have, in this case, the derivative here will be high, and so in this case means that it will move faster. And when the norm is small, so we use in this case this inequality, when the norm is small, the derivative will be small, and so the evolution will be slow. What is the consequence of this result? In some sense, this means that when we start with the small initialization, we have a lot of slices such that the norm is near to zero, and this means that the derivative will be small, and so the norm of these slices will be near to zero. Norm of the slice near to zero, this is like we have a regularization towards structured sparsity. Let me go to the figure. So this means that if we take a slice, so is a matrix, the norm of this matrix will be near to zero. This means that, okay, all this matrix, the value of this matrix is near to zero. And so we have a regularization toward sparsity. Why it is structured? Because all the value of the slice will have a value near to zero. We don't have independently value equal to zero, but we have all the slice which is equal to zero. So in this case, we can show regularization toward sparsity and towards structured sparsity. We can ask the question, what if this structured sparsity implicit regularization can lead to rank implicit regularization toward the rank of the tensor. And we have the following results, that when we have a structured sparsity, we can approximate the tensor by another tensor such that the multilinear rank is small. The structured sparsity of the core tensor implies a low multilinear rank of the constructed tensor. Okay. So this is interesting because we show that in deep CP factorization, we have implicit regularization on another notion than rankness, which is sparsity, but the sparsity is structured, and because the structure of the sparsity, this will lead a regularization on the rank. If we have sparsity, but it is not structured, this will not necessarily induce a regularization on the rank. But the structured sparsity allows to obtain this result on the implicit regularization of the multilinear rank of the tensor. And here are some experimental results to illustrate these theoretical findings. So we have synthetic data. Here we consider three-ordered tensor, multilinear rank. So this is dimension 10, 10, 10. The multilinear rank is equal to 3, 3, 3. Okay, and in this figure is the evolution of a slice of the core tensor. during gradient descent iteration, and we have the depth from 1 to 4. So this is the result with depth equal to 1. And you can see how we have here many norm of the slices with high value. We increase the depth. Here we have, okay, some of them. Each time we increase the depth, we have only small number of slices which will emerge during training. And this means also that we have structured sparsity of the core tensor, since many tensors will have a norm near to 0. This is a similar result, but on the eigenvalue of the transition matrices. So this is show that is to show that the structured sparsity is related in this case to the multilinear rank. So we consider here the singular value of the matricization of the core tensor, and you can see that when we increase the depth, for example, here, here, only a small number of singular value will emerge. Depth is equal to 0. We have a lot of singular value will emerge. When we increase the depth, only small of them will emerge. Here's similar result, but when we consider different experiments with different initialization. Also here the color corresponds to the generalization performance. And this result also confirms the effect of depth. As you can see, when the depth here is equal to 4 or 3, so the learning, the algorithm will converge to solution such that the number of vector with high norm is small compared to situation when the depth is equal to 1 or equal to 2. The previous result was on simulated data. We also tried real data experiments, and we observed also similar results, that the depth in general is so that the implicit regularization is more pronounced when the depth is high. So to conclude in this work, in this talk, I showed how we can characterize implicit regularization in deep tensor factorization using a dynamical analysis of the learning. And I showed that the implicit regularization is more pronounced with a larger depth. Also, this implicit regularization can be toward the structured sparsity, and which induce implicit regularization toward the multilinear rank for Tucker factorization. And in general, so I showed how to combine tools from tensor analysis and tensor decomposition, and also tools from dynamical analysis to try to understand the phenomena observed in deep neural networks. So this is the end of my talk. So I will stop here, and feel free to ask any question. Thank you for your attention.
Yeah, thank you very much. Any questions or comments? Yeah, it seems not. Yeah, all right, okay. Let's thank you again, Hachem, for the nice talk, and thanks everyone for coming. I guess just see if there is no one else. All right, okay.
Thank you,
Yeah, thank you very much. Yeah, so looking forward seeing you in person at some point. Yeah.
Yeah,
All
sure.
right. Take care. Bye-bye. Bye.
Bye.